Shall we get started? Shall we get started? Okay, first day of work. First day of work, you show up. You are hired by, pick your favorite employer. Who has a job already lined up? Where's your job already lined up? NVIDIA, very applicable. Okay, so you show up at NVIDIA on day one, and you walk in, and your boss says, John Danskin, and let's see, who else are lead architects there? There's Danskin, there's Jonah. All of the lead architects decided to take the year off. You're working on the 11 series chip. You are in charge. So, and that's all they tell you. They tell you, you're in charge. So, what questions might you ask if you show up on day one of your job and they say, you're in charge of the next chip, you have $1 billion to develop it, you have 18 months, here is your team, go build something. What questions do you begin to ask? In this case, if it's NVIDIA, do you ask Jensen? What do you ask Jensen? Yes? What is it intended to do? Like, what is the workload? Because we've seen in many cases that if you knew your workload, you might make very different design decisions. For example, on assignment 2, if I gave you a render or a scene that only had 3 really big circles, and that's all it had to render, you might make very different design decisions than if I gave you random 100K. Now, of course, in assignment 2, we would like you to come up with an algorithm that is sort of doesn't really worry about that too much and works well for both of them. But okay, so that's a reasonable decision. And let's just say, okay, so you use the example NVIDIA. So clearly, NVIDIA these days cares about 3D graphics, computer vision, machine learning, and deep learning. Those are your workloads. Okay. Anybody else have a different job with very different workloads? Nobody else has a job. It's tough market out there. Okay, so that makes a lot of sense. But here's the question. So let's say that they say, here are the applications that your chip needs to run really well. So with the example of NVIDIA, I think we understand that pretty well. So then the question becomes, well, how do you know? In 18 months, maybe you make a deal with your boss. You say, okay, if I do a good job, I want $1 million a year base. That's what you ask for. And if I do a bad job, you can fire me. A lot of people get fired in the examples in this class. So how do you even begin to think about what a good job even means? What are the metrics for a good job or a good design? What are some metrics that you might think about? Sorry? Throughput. So it might be like we want to evaluate n images per second or something like that. Okay. But I can make my throughput arbitrarily large if I decide to use the United States' largest supercomputer to perform this task, right? So throughput is a good metric, but may not be the end of the story. Yeah. So there's some notion of cost, which in this case, if we're talking about computer architecture, it could be chip area, could be chip power. It could be like actual cost to manufacture, which usually is proportional to area. Exactly. Okay. What are some other ideas of metrics that we might use? Yeah. Thermal efficiency. So yeah, that's another, so you guys are moving into efficiency. So one metric would be, what is the absolute performance of the chip? Right? We would like to win this benchmark, and at the end of the day, a lot of these benchmarks in CNET or whatever are going to say, here's the bar for one chip, here's the bar for another chip, this bar is higher. So absolute performance still very much matters. Like, for example, these days, if you're doing a lot of machine learning computations, you care about how long will it take me to train my network. Like, that's the only thing you care about. So that's absolute performance. We talked a little bit about speed up. So you could say this design is good if, as I add more resources, I get proportional amount of benefit. So if I go to 5 cores, or if I go to like 8 cores over 4 cores, maybe I get twice the absolute performance. That would be good speed up. That would mean that the architecture scales. And then, of course, some of the things that you all have already mentioned is we might care a lot about efficiency. It doesn't matter what your absolute performance is if you have a $1 million chip to get that performance. Exactly. Okay, so today I'm going to talk a little bit about ways to think about how are you doing well. Different ways that we might grade your assignment, even though you know how we're grading your assignment. And different ways to start debugging programs. And then next time, we're going to move right into designing chips. So it's next class is going to be a big change. Okay, so let's think about this question maybe, does it scale? Because like we're in a parallel systems class. It scales is sort of that's a good thing. So let's think about measuring scaling. And let's go back to this example we spent some time on a class ago, which was I wanted to bend these particles into this grid. And I gave you, just to recall, I actually gave you, I think, 4 different implementations of this thing. And the algorithms changed dramatically. The amount of work done by the algorithms changed dramatically. And so would you say that if we were to measure speed up of this program, let's say that your boss came to you and gave you like some C code, just like here's the program it has to run. You can change the program however you want, but here's the original program. Do you think that it's fair to measure speed up in terms of the parallel program that then runs on a bunch of cores? Or should it be measured against whatever the version of the program is that runs best on one core? So for example, if you recall this very data parallel example of solving the problem, which was similar to your histogram on the homework, or sorry, on the exercise, if all you were supposed to do was run your program on one core, you probably never, ever, ever would have written this program. So what do you think the right comparison is between, like, if you're trying to say, I did really well because I now have this system that scales out to 16 cores or 32 cores, what would you compare it to? Because remember, speed up is always this ratio. Yeah. Exactly, and this is a pitfall that a lot of even really smart people tend to do. We will see academic papers published in great conferences all the time, where they'll make a very beautiful speed up curve, and they're comparing to something that is very far off of what a good person would have done on a small machine. So it's something to keep in mind when you start talking about I did a good job. Now on your assignments, we're defining what a good job means. But on your final projects in this class, it's your job to define what a good job is, right? Because I'm not going to know what algorithm you're using. I'm not going to know what application you're doing. But I am saying, hey, if you want an A on your final project, you have to convince me that you did a good job. So you're going to have to self-assess your speed up. And a lot of the times, for example, I'll see projects that are like, hey, look, here is a very simple application. Here's a single-threaded piece of C code. It runs this fast. I went and ran it on CUDA, or I re-implemented it in CUDA. It ran this fast. And now the GPU must be 800 times faster than the CPU. Therefore, I deserve an A. I made it 800 times faster. But we all know that the GPU only has 7 times more resources, or 8 times more resources than the CPU. So that should suggest that our original baseline was pretty poor. So these are the types of things that we're going to think about in this class. So imagine that you're not going to go work for NVIDIA. You're going to go work for some fictitious company that the only thing they care about is not graphics or not bitting particles into cells. But I'm going to go back to the grid solver example from the class. The only thing that they care about is winning the grid solver market. Okay? And so you come back in 18 months after spending $1 billion on development, and you give your boss this graph. So you built a bunch of your chip, 0 to 32 cores. And I'm plotting linear speed up here as the y equals x line. So what do I mean by linear speed up? It is the ideal expected. So if I'm using P processors, it should be P, x equals 1. And you come back and you say, well, boss, you told me that I needed to run my program to execute the grid solver on a grid of size 258 by 258, pretty small grid. And this is the speed up curve that our system obtains. Are you going to get fired, or are you going to get the $1 million base? What do you think? Should we fire him, or should we give you $1 million base salary? 500,000. You're a generous boss. No, but what do you think? What's your reaction to this graph? Sure. Why don't you defend yourself? Okay, so you're saying that well, hold on. Okay, so you're saying not my problem. Okay, what about anybody else have, you know, like you can, this is the celebrity 418 apprentice. You make the decision. Yeah. Well, that's a great question. That's what I'm asking, right? The whole point of this lecture is how do we know if we're doing well? So what do you think? What are you dissatisfied with in this graph? Yes. Yeah, I'm not going to get into the details of why it's slowing down, but maybe a simpler question is why the heck is it not up there? At the very least. You can ask, like, why is it not up there? And oh my gosh, what did you? There's a lot of processors, a lot of cores. Well, it is. That's what the graph says. Okay, so let's think about this problem a little bit. And remember, this is the grid solver, and we decided a couple lectures ago that we were going to partition the work across the processors in tile major order. So I'm drawing so each one of these dots is a grid cell, not a particle, a grid cell. And I'm splitting up the grid cells in tile major order. And can anybody recall why I did that rather than choosing, let's say, a row major order? Yes? That's right. So just to review, remember we have n squared elements partitioned amongst p processors. So every single element, every single processor needs to do about n squared p over p work per iteration. It needs to do its share of the work. And that it needs to communicate information on the boundary of this region to its neighboring processors, which this length is n over root p. So the amount of communication is on the order of n over root p. So the ratio of work performed to communication would be n squared over p divided by n over root p, which means it goes as 1 over root p. So as p gets bigger, our arithmetic intensity goes down, right? Which is what you'd expect, is the area, the ratio of the area of these tiles to the perimeter is beginning to shrink. Okay, so in light of that, who can begin to explain why performance might actually go down? Yes. Tile sizes are much smaller. The arithmetic intensity is dropped, and so I just have less work to do for the amount of communication. I have more communication here than I have here. And so it's, you know, it's not shocking that maybe that communication might just begin to outweigh the fact that we have more processors. Good. Okay, so let's say that that's the first graph you show, and then like your boss is just about to fire you. And then you show your boss this graph. Same graph, except I'm plotting multiple lines. And the difference between the lines is the size of the grid. So n is getting bigger as the lines are going up. So what do you notice here? So has your team done a good job on meeting the demand? Yeah. Right. So in this first example, as you claimed, is that like the small problem size is just so small that you never really be interested in trying to run this tiny little problem on this huge machine. And if you were, then you would have had a bad solution. Like if for whatever reason, like that was what we cared about, then that would have been a bad solution. But oftentimes the reason to parallelize, to get a big machine, is you want to work on a bigger problem. And then the question becomes how efficient is your solution on problem sizes that are more realistic of what you'd want to do with one of these fancy parallel machines. Exactly. Okay, So let's say that you did this, and so n, the biggest n there is 1K. And let's say you're like, okay, we're doing well, but really what we care about is the marketing team says, now you can run on this grid that's bigger than you've ever run before. Like we've got this fancy 32-core processor, and you come back with this graph. Now at this point, do we give you the million base, or do we fire you for being a liar? So what's going on here? Yeah. Well, that's what I'm asking you. Are we going to fire him because he's a liar? What? Okay. Well, let's think about this a little bit. You believe this? No, don't. The first row does not believe this. You believe it. You don't want to be fired. Do you have a justification for your graph? Is this an alternative scaling curve? Yeah. Well, these are all the same size. This is the 12K by 12K, and the only thing I'm changing is the number of cores. That would look the other direction, actually. Okay. I don't buy that. Okay. You wanna save your friend here? This is the exact same code. Like in this case, this is the exact same code. You kind of know what it looks like because we went over it in lecture. Every processor gets its own region. And then, okay, so the mystery here, they're actually, oh, yes. Oh, but that's a pretty sizable difference. I wouldn't say that that's measurement error. So let me tell you what's happening here. So think about what's happening as we increase the number of processors. The amount of grid elements per processor is beginning to drop. And over time, it gets smaller and smaller and smaller. So what's happened here is like right at the 16 processor point, if you took n squared over 16, all of a sudden that working set's starting to fit in cache. So and there's a detail here is in this particular processor that they're testing on, as we replicate processors, we're also giving them L1, L2 caches, right? So I'm not just actually replicating execution capability. I'm also replicating all the storage that goes with it. What you're seeing here is this superlinear speed up that's occurring as soon as one of the working sets starts to fit in a major cache in the machine. And so in that case, things are going a lot faster. So the point of this sort of intro is that you have to be careful in assessing whether or not you've done a good job, and that the size of the problem in relation to the size of the machine can have very significant impact on what your charts or what your data tells you is actually going on. So evaluating a machine, a design, with a single problem size can be problematic because, well, if that problem size is too small, then you just can't fill up this big honking machine. Like, for example, if I asked you to add up two 1,000 element vectors or do some operations on two 1,000 element vectors on a GPU, that's just way too small for a GPU. You need tens of thousands of things to do on a GPU. There's just no hope. Conversely, imagine I ask you to run this huge simulation, and it requires more memory than one machine can actually have. So you'd have to thrash to disk. Whereas a parallel machine would have a bunch of different memories, like a cluster would have a bunch of different memories, and all the data in the problem could actually be held in memory, and then you could get like a big superlinear speed up, like what we're seeing on the previous slide. So, and in general, the reason to use, one reason to use a big parallel machine is to work on bigger problems. And so often you're going to see the goal of buying a bigger machine to compute more rather than just get something done in a fixed amount of time. And also, I want to point out, especially for those of you working at Intel or NVIDIA or Samsung or Qualcomm that are actually going to be interested in building chips, scaling down is actually as much of a concern as scaling up. So they might design an architecture, like for example, this is not the 10 series architecture, but these are all pictures of the 9 series NVIDIA architecture. When they design their SM core, they say, hey, look, I need to be able to use this design in the really expensive 20-core version. And I also need to make sure that my design decisions work really well in the mobile embedded space, because efficiency of human capital means that we cannot create a new design for the low end and the high end and the middle. So when I say scaling, I'm actually thinking about scaling up to large machines, but also scaling down to the low end of mobile processing. So it's actually not that easy sometimes to kind of scale a problem up in a way that's meaningful. So if we took, for example, the grid solver, the problem size is not just the grid size itself. There's actually a bunch of little details in it. For example, I can increase the grid size, which I did on those charts, but I could also change the convergence threshold of the solver, which might mean it needs to iterate more. I could change the time step size and simulate in the ocean, or I could change like the total amount of simulated time. Like if I was supposed to simulate 1 day of ocean currents, that's a different problem size than simulating, 1 hour of ocean currents, because it's just less work. So there's a lot of different ways you can think about scaling. You can say, well, okay, I'm going to increase the number of particles per processor, the number of grid cells, or the number of circles. Or you can kind of think about things in a very system-oriented way. You can say, I'm going to keep the amount of memory the same, or I'm going to compute the amount of work the same, or change that, and so on and so on. So I'm going to talk about some of these examples today. Okay, so let's think about, hold on 1 second. No, so we have to go through some examples first. So here's an example. Let me go back to this. If you were going to try and scale up the grid solver, which parameter do you think is actually the easiest to scale? Like, which one makes the most sense? So you could say I can make the grid size bigger, but it's kind of tricky, right? Because if you make this grid size bigger, you actually mean that you're going to create more work to convergence. So the problem, the amount of work that the code is going to do is actually going to be nonlinear in n squared. In fact, it's actually O of n in n squared. So if like the amount of work done is n cubed. So you might like say, I'm going to make the problem size bigger, and then compare it on a new machine, and not realize that the program takes longer now to actually run. Another example would be, okay, let's actually change the big capital T. Let's just run the simulation longer for more time steps. That might make a lot of sense. And that might be an easy way to have a much larger program run. But this variable changing doesn't impact how we parallelize the thing as well, because this is just a sequential dependency. So I just wanted to point out that it can be kind of hard to scale things up or down. Okay, so first of all, let's talk about the simplest version of scaling, which is the one that we've talked about in class. Is we'll define speed up as the ratio of the time it takes to get the job done on one processor to the time it takes to get the job done on P processors. So we were saying we were doing the exact same problem. We were doing it on more processors. And if we get a speed up, ideal speed up is basically P, the number of processors we're throwing at the problem. And you'll often heard this called hard scaling, keeping the problem definition exactly the same. We are trying to use more processors to compute faster. That is the definition of hard scaling. So what are some examples of when we care about that? So one example would be assignments 1 and 2 and all the other examples we've talked about in class. What are some other examples of why you'd want to use a bigger machine to solve the same problem faster? Maybe. So here's an interesting question. Is 10 years ago, I could play Quake. Quake ran at 30 frames per second. Is the goal of all GPU development now to run Quake at 3,000 frames per second? So that's actually a case of a different kind of scaling that we care about. In fact, it's the scaling on the next slide. So what are some examples of, I need to have more cores because I want to get something done faster? Yeah. if you want to run large simulations in general, sometimes you're doing that because I just need the answer back faster. DNA sequencing, so it's a big problem of mapping the genome. We need to use a bunch of machines, get it done. That sounds plausible to me. Yeah. Real-time image processing, in what context? Correct. So in some sense, you might say I want more cores to get me to 30 FPS. But once you hit 30 FPS, does it make sense to go to 1,000? Sometimes it actually might. So robotics is a good example of, I think, either of, it could be, yes, I want to run the same problem faster, so it's real time, or super real time, because a self-driving vehicle wants the answer in less than that, probably. Sure. But then you could also say that graphics and anything real time might actually be interested in this other form of scaling. So I don't care about running the same problem in less time. I care a lot about doing something more advanced in a fixed amount of time. So time-constrained scaling is the work done by preprocessors versus the work done by one processor. So the amount of work I get done in a fixed amount of time is the notion of speed up. So what would that example be if we went back to graphics? So in a fixed amount of time, I have to render a frame in 30 times a second, right? Or 60 frames per second if I'm a first-person shooter. If you give me a bigger, fancier GPU, what does that turn into? More detail. It's a more complex problem, a higher resolution image or something like that. So let me give you a quick example. So one example is, if you take the top right, this is Half-Life from 1998. That's what it looks like. It ran at 60 frames per second. This is Assassin's Creed from 2014. Notice that the frame rate here is exactly the same time as up there. We still render frames in the same amount of time, but the problem is much, much more complex right now. Much more detail, much better lighting, much better shading. So we've turned a decade of fancier GPUs into orders of magnitude more complex problems that can get done in the same amount of time. Here's another example, actually. It was one that I learned about last year, which is kind of interesting, is the astronomers build really large telescopes. So this is an example of your real-time robotics, even though it's not robotics. So the LSST is this telescope that will be completed in a couple of years, and it takes a 3 gigapixel image every 15 seconds, which sounds big. It's actually not that big when you think about how many images are uploaded to YouTube and stuff like that these days. It's actually not that big. But it is kind of big in that you have to do some image processing on a 3 megapixel image in 15 seconds. And this data is coming off the telescope, and so you have, every time a new image comes in, you have about 15 seconds to do whatever image processing you can do before you store it off to disk. And the minute you store it off to disk, it's going to take a long time to bring it back. And so they're very interested in how can we do more and more sophisticated analyses to sort of detect anomalies or whatever, so that in that 15 seconds we can quickly analyze the image, figure out if there's anything interesting in it, and then alert a bunch of other telescopes around the world that could actually start paying attention to that part of the sky. So that's an example of, if you can do more in 15 seconds, if you had a whole cluster there to do more in 15 seconds, maybe the number of false positives and anomalies or something like that goes down. Because whenever you call a telescope up on the top of a mountain in Hawaii to do something, it's probably not free. So that's another example. So what are other examples of this notion of time-constrained scaling? We have a fixed amount of time to get something done, and more processing will allow us to do cooler stuff, to do more sophisticated stuff. Who cares about these kinds of problems? The high-frequency trading people care a lot about this kind of stuff. They want to run the most complex model that they can and get the answer back to make a buy-sell decision in milliseconds, right? Exactly. So a more sophisticated model, being able to run in a fixed amount of time, presumably will result in better trading decisions, and so on. Sorry? Oh, yeah, search engine is an excellent example, is that there's a lot of evidence that if you don't get an answer back to a human being in a fixed amount of time, like 50 milliseconds or something like that, that they lose interest. So Google could return almost certainly much better results to you if they waited for a second or two, but they don't. They say that, look, all the evidence points to humans becoming disinterested if they don't get the answer back quickly. So any kind of search or e-commerce as well is very, very time constrained. Yeah. That's true, but I think in the Google there's a threshold. Like the HCI studies have shown that you have basically until this amount of time before human behavior starts to change. So going faster than that threshold is not necessarily noticeable, and also probably runs you right into network latencies and stuff like that. So yes, I mean, sure. What do you mean by surgery? Yeah, I can believe that. And another one might be we could actually bring graphics into it. We can say any kind of like virtual surgery or any kind of virtual interactions. Like in VR, for example, it's very clear that if the answer doesn't get to the human's eyes within about 25 milliseconds, the human will start throwing up. And so any kind of online or real-time system is often very time constrained. So to go back, so some examples: computational finance, modern websites, real-time vision, or any kind of real-time systems for robotics. Let's see, that was right there. Yeah, okay. So another example would be memory constrained scaling. So memory constrained scaling is a little bit different. In memory constrained scaling, the idea is not I want to do the same problem faster. It is not I want to do more work in a fixed amount of time. It's largely I want to work on bigger problems. And so by adding machines, I get to work on bigger problems. So this is a big example. A big example of this is in data processing for analytics or for machine learning. One of the reasons why large clusters are used to do these types of problems is because you have to have a large cluster to hold the data set. One machine would have to be working off disk, and if I get a bunch of machines, I can just partition the data across all those machines and run completely from memory. It's also a major motivation in scientific computing, and I have that on the next slide, is that the data sets are just so big, you need a bunch of computers to actually just hold the data in memory. So you can think about memory constrained scaling as the work per unit time on P processors versus the work per unit time on one processor. Because now the amount of time that I run on P versus the amount of time I run on one is different, and the size of the problem is different. So I can't compare just runtime, and I can't compare work done. I actually have to compare rates. Work per unit time with one processor, like how many transactions per second, versus work per unit time on a bunch of processors, how many transactions per second. And this is often called weak scaling. So strong scaling is keep the problem size the same, add more processors. Weak scaling is scale the problem size with the number of processors. So the amount of memory per processor is about the same. So these supercomputing guys, some of the reasons why we have such big supercomputers is not necessarily because the computations are extremely expensive. It's because the data sets are insane. And so I started this lecture with that example of I want to put particles into a bunch of grid cells. And imagine that if you didn't have like 1,000 particles or 100,000 particles like in your assignment 2, but you were doing a very large galaxy simulation. And that very large galaxy simulation had a lot of particles. And so you can imagine how much memory you need to hold the state of one of these simulations. And that's why one of the reasons why these supercomputers are so large. I believe that's a teraparticle simulation, and that's back in 2012. Right? So we've moved on about 5 years from that. So holding teraparticles is a lot of memory. And in any of these large-scale machine learning computations where you're looking through clickstreams of Amazon or Google, the cluster is there just to hold the data set in memory. So more servers. Oh, and also actually, like Memcached, if anybody's familiar with Memcached, if you've worked at Facebook or a web services company, the reason why those deployments have so many computers is what? You're just trying to make the biggest memory cache you possibly can come up with as well. So I've spent some time myself at Pixar, and all of these metrics come into play at Pixar as an example. So they have a situation where, like, their artists are saying, look, render me the final 1 minute of this movie. And that's very much a problem-constrained situation. They're just like, I want to see my movie clip that I just animated, and I want it as quickly as possible. So use as many machines as you can to get this sequence of things done fast. Then you have like artists that are actually trying to do animation or to do the lighting and shading calculations, and they actually want to work interactively. So they want to do something in the UI, and then they want to have the result come back to them immediately. So they're working in a time-constrained scaling scenario. So Pixar will buy its artists, like the biggest, fanciest computers in the company, so that whenever they do something, the answer comes back at 30 frames per second or 15 frames per second. So it's about doing more in a fixed amount of time. Then if you've watched any recent animated movie, you'll see huge simulations of fire and smoke or water or whatever. And those are very much like this situation back here, where those simulations are just these huge simulations, and they need an entire cluster of machines just to fit the simulation in memory. So all of these different examples pop up just in making a movie, for example. One of the interesting things is that for every movie, they usually sort of, or up until recently, they just restock the whole cluster, right? Because a movie comes out every 2 years, and about every 2 years is probably when you want to rev all your machines. And the way it works is they actually figure out kind of what they want to render. They figure out how much money they can buy for memory. And then the entire production is basically just limited. The scene complexity is limited to how much memory they have in the cluster at that time. So if they're saying, like, if the director's like, this thing needs, there's going to be a lot of these complex outdoor scenes with all these trees, then the tech guys would be like, well, how much memory do you think you're going to need for that? And that's roughly what they try and stock the cluster out for. So it's a memory-constrained scaling example. Are there any cool examples from your own internships of thinking about different types of scaling? Especially like memory-constrained scaling. Any of you have done anything in internships on really big data sets? No? Yes? Ah, Amex, okay. So you had all credit card transactions from the United States for 10 years. That seems like it would be a large data set. How much data was it, you said? Terabytes? Terabytes of text is a lot of text. Yeah. 120, okay, so 125 peta of what? Of what data again? Oh, yeah, okay, from CERN? Okay, yeah, they generate a lot of data at CERN very quickly. And so in that case, like, even if the computation is really simple, you need it in memory to be able to do anything, yeah. Especially any kind of machine learning that's going to iterate over the data a bunch of times. Any other cool examples? Anybody worked on something larger than 125 petabytes? It's a pretty high bar. Cool. What were you guys doing with that data? Uh-huh. I see. So you were trying to do parallel I/O. Cool. Okay. So speaking of scientific communication, let's think about the scalability of this grid solver problem. And let's think about which way is it easiest to scale this problem. So let's think about the execution time and arithmetic intensity under these different scenarios. So the first one is this problem-constrained scaling scenario, which is probably the easiest. So the execution time, assuming that we parallelize perfectly, goes as 1 over p. Makes sense, right? If we assume that if we scale linearly, which if I went back to the beginning of the lecture in the large grid example, it was starting to scale pretty linearly. is if the execution time is 1 unit of time in the one processor case. In the P processor case, it's 1 over P units of time. The elements per processor is n squared over P. And that makes sense by just this figure right here, right? Okay, so the communication to computation ratio, I'm saying is 1 over root P. And where did I get that from? I'm ignoring n here just to. So where did we get the 1 over root P? Or sorry, not 1 over root P is P of the root P. Because it's not arithmetic intensity this time. It's communication to computation ratio. So we had communication, which was n over root P, divided it by elements computed. So I had root P over P in the denominator, and I got square root of P. Okay, so now let's think about some of the other options. So let's think about time-constrained scaling. Let's say what we wanted to do is we wanted to, as we added more processors, we wanted to keep the total runtime the same. So imagine this is like a video game now, and we're trying to actually simulate fluid at 30 frames per second in a video game. So I'm really asking you, if I give you a bigger GPU, more processors, how much bigger of a fluid simulation could you have done in that same amount of time? So let's look at that a little bit. So the math is going to get a little tricky. So the execution time is going to be fixed at n cubed. And I forgot to mention that for this n by n grid, on average, you can think about it as it needs n iterations to converge. So if I have n squared grid cells, I have O of n cubed work. N iterations, each of which is n squared. Okay, so if the execution time is fixed at O of n, n squared, at n cubed, and remember, time-constrained scaling, we've got to keep that the same. So imagine that there's some bigger grid k by k that can now be computed in the same amount of time. So, well, what's k? Well, I know that if things are being sped up linearly, the total cost of the parallel computation is k cubed work over p. And k cubed over p has to equal n cubed because, by the very nature, this is the time for the parallel computation. This is the time for the sequential computation. So I just solve for k, and I say k is n to the third root of p. So this is how much bigger k is than n. It goes as processors to the cube root. Okay, so now the elements per processor, well, it's k squared over p, right? Because we now have k by k grids, divided it by p. And if I just substitute in the elements per processor is n squared over p to the cube root. Just doing a little bit of algebra there. And then the communication per processor is going to be k over square root of p, which is 1 over p to the 1/6. And if I divide communication by elements computed per processor, I figure out that now the communication ratio, which used to go up as the square root of p if I kept the problem size the same, now as I add processors and grow the problem size, the communication to computation ratio increases much more slowly, which makes sense because I'm adding the same number of processors, but I'm also making the problem size bigger. So from this, you should be thinking, oh, if somebody told me to scale linearly by making by the definition of time-constrained scaling, it should be a little bit easier for me to do that than to do that in the hard problem-constrained scaling case. And we can go over the same thing for the memory-constrained scaling example. So in the memory-constrained scaling example, I'm saying that the grid size should be n to the root p times n to root p. That's the size of my grid. And why is that the size of my grid? How did I get that? Memory-constrained scaling. My original grid used to be n by n. When I go to p processors, my grid is now n times square root of p on a side. Why does that fall directly out of the definition of memory-constrained scaling? I'm making the grid p times bigger, and then I'm keeping the partitioning square. I'm keeping it square. So the scaled grid size is n times root p on edge. The execution time is just the size of the grid cubed divided by the number of processors. So I just took n times root p, raised it to the third power. I cubed it because that's the execution time for that grid size, and I divided by p, which was because of the linear scaling, divided by p processors. And then the elements per processor is just fixed at n squared because it's the same. When I add more processors, I just add to the grid size. So the communication to computation ratio is actually fixed. So it's actually pretty easy to do the memory constraint scaling in this case. Just adding more processors doesn't induce any kind of global communication at all. It's just I still have to communicate the same amount of data to all my neighbors, and scaling just is pretty easy. Okay. So as I alluded to at the beginning of the lecture, it can be kind of tricky to scale a problem size. Like, for example, increasing n in the grid solver makes it harder to converge. Changing the number of particles in a particle simulation often changes the required time step size that's needed. So you will, as you begin to scale things up or down, you are going to probably need to understand a little bit about how these applications are working. Otherwise, you could get yourself in big trouble. So the summary of this first part of the lecture is basically just be careful. And if you're trying to report on whether or not you're doing a good job, you need to think about what factors are in play. And this is what you will be examined on in your final projects. Because if I will give A's to people that did a good job, but also convince me that they did a good job. Because remember, I don't know the answer to your problem because it's your project. So let's go back to that hypothetical job now. And we defined our problem. We gave our engineer $1 million or $1 billion to engineer a solution. And would you go about solving this problem by building a chip, seeing how it goes, and if you don't like it, go build another one? How would you begin to de-risk this design exercise? So how are you going to test your idea? You have a chip design. You have an approach. You have a parallel algorithm. How are we going to tell if it's good without actually building the chip? Sure. So you could actually do some back-of-the-envelope calculations. You could say, just like on a homework assignment or in problem 1, we're going to go compute the bandwidth needed and the compute intensity needed. And I'm going to see if on my theoretical chip I'm bandwidth bound or compute bound. Yeah, that's actually probably the first thing I would do. And let's say if those numbers check out pretty well, now what? How would you go to the next level of detail of figuring things out? Anybody else that's done any ECE work? So we have a design. We have a hypothetical chip we might want to build. We can either go build it. We can go spend $25 million and build it. And if it's no good, we'll throw it away and start again. Or we might be able to hopefully not have to do that. Okay, so first of all, you're saying, well, we're going to start simulating the thing. So let's go simulate how this modern architecture works. And so if you took a proper computer architecture class, you would do this kind of stuff. You would design an architecture, and you would simulate its behavior. So there's a couple different ways that people do simulation. And you can imagine that there's this trade-off between really accurate simulation and very, very coarse-grained simulation, like an arithmetic intensity computation on the back of an envelope. So if you go over to Brandon Lucia's research group, if you go over to our new faculty member, Nathan Beckman, they do a lot of their architecture research on simulators. And those simulators, they have written programs that execute your programs and keep statistics of what the machine is doing at this time. So you could have an execution-driven simulator that just flat out executes your program on a virtual processor. And if it needs to be 4 cores, they will simulate 4 cores. Or if they want to simulate 2-wide superscalar execution, they can put that into the simulator. They do all the things that we've talked about on the whiteboard in a program. More common, especially these days, because simulating a processor that's built into silicon can be quite slow. Another strategy, and this is a number of folks have used this to do projects in class, is you can use a tool that instruments regular code running on a regular processor to generate statistics about that code, and then play those statistics back in a simulator that can't actually run programs. So PIN is a very interesting tool that was created by Intel, and it goes into your binary and wraps every load and store instruction with some logging functionality, kind of the same way that Valgrind or something like that does for your memory accesses. So if you run PIN on your binary, what you'll get out is you'll get out a log saying at this clock cycle, this address was loaded from or stored from. And then that log can be actually played back through a memory system simulator in order to figure out how fast a particular memory system might have actually been able to service those requests. So Professor Mutlu's group, Professor Mutlu is no longer at CMU, but he had his whole research group on design of memory systems and memory schedulers. And so they would take these massive traces and run them through their memory system simulators. And some of those traces were created from real-world or were definitely created from real-world applications. Like, for example, I think last year, some students generated some traces of some parallel code, real programs running on their laptop, and then played that back through a simulator that they created for their final project. So they were trying to implement some of the architectural ideas that we talked about. And if you have such a simulator, you can try all of these different designs. So now on this graph, every blue dot is a different architectural design, maybe a different number of cores, maybe a different type of ALU, maybe a different clock rate. And what the diagram is plotting in the y-axis, it's the energy efficiency. So you guys gave me all of these metrics at the start of lecture about what matters: performance, efficiency, energy efficiency. So here on the y-axis is the energy efficiency in terms of joules per operation performed of these different processor designs. And here is the space density, the operations per second per millimeter squared. So if I'm moving in this direction, if I'm moving in this direction, I might be running faster. I might be moving in this direction as well. But as I move in this direction, I get more performance for my chip. But the energy cost also goes up. So where are the best designs? Given this diagram, where do the best designs lie? So it's this bottom right curve, which is called the Pareto curve. The Pareto curve says that there is no design better than this design in any of the one axis. In either axis. So I cannot move down without sacrificing efficiency. Or I can't move to the right without sacrificing energy efficiency. So if you're way over here and you're saying, I want the most compact chip possible and I'm willing to burn energy for it, you might take these designs. If you're saying here, I'm like, I want this small energy efficient embedded chip that might waste some space. Sorry, large, like it might waste some space, but it's really energy efficient. I might take these designs. So by simulation, they can simulate all these data points and figure out where the most optimal data points lie. And so every year there's a couple of good projects where people get interested in the architectural features that we're going to start discussing next class and actually simulate them all and act like an architect. Here's a question. Increasing the clock frequency of the chip moves in which direction in this diagram? Increasing clock frequency. So does it move me up? Yes. Does it move me this direction? Why does it move me this direction? Because I get more operations per second. So increasing clock frequency is going to move me in that direction. Exactly. Okay. So the problem, and the reason why I started this lecture with scaling, is that imagine you go to simulate the behavior of this application, and you want to run the supercomputing simulation, and you're trying to build a new supercomputer. Well, if you think it takes a supercomputer a week to perform this computation, how long do you think it's going to take your software simulator of the supercomputer? It's going to take an incredibly long time. So scaling problems down is something that we do all the time in order to be able to simulate them or to be able to actually debug them if we were just thinking about software. So for example, how many of you have observed incorrect behavior in assignment 2 and wanted to know what was going on? And the problem that made it hard is that you just couldn't put a breakpoint on one thread. You had all these thousands of threads running at once, and you had results on thousands of pixels. And so your first reaction would have been, okay, let me put a printf and have every thread print out the results, right? And you just get an interleave mess of 1,000 different things, right? And most of the time, what do we tell you is we say, well, can you isolate it to one thread's worth of behavior, or maybe could you work on a really, really small data set? For example, a data set that had 2 circles in it, or 1 circle in it, rather than all the circles. Or a data set that had 10 pixels in it, and all the circles rather than all the pixels. So essentially what I'm telling you is I'm telling you to scale down your problem. Right? So imagine you take the original image, and you're like, okay, the printfs are a little overwhelming. I'm going to run on a smaller image. So I'm going to take the exact same scene, and I'm just going to take this image size, let's just say it's 8 by 8. Your image size is 1,000 by 1,000. I want to scale it down to 4 by 4. Does this concern you at all about maybe we kind of just changed the problem a little bit on us? So in assignment 2, what is the salient metric that really kind of gets you thinking about, okay, should I do it this way, or should I do it this way, or whatnot? Yeah. It could be the number of circles, but I would say that having 10,000 circles is not that big of a deal if the output image is 10 gigapixels, right? So what is the real salient metric then that really makes the problem tricky? Is it number of pixels? Because it could be do I care about the number of pixels if I'm only rendering 1 circle? There's something a little bit more nuanced here. So what is it? Or it's kind of like the number of circles per pixel, or maybe like it's the ratio of number of circles to number of pixels, right? In some sense. And so by just scaling this problem down, I just change that ratio. So the results, the decision that I make to do this problem well, might be very different than the results I make to this problem well. So can someone think of a better way to scale this problem down that doesn't necessarily affect that as much? How could you make a very simple, like if I said I only cared about, yeah, one second. So yeah, you could say, you know what, I can actually just, let me assume that there's a uniform distribution, and let me just kind of go see what's going on in one tile or one quadrant. And maybe if I'm not certain it's a uniform distribution, maybe I could choose 1 or 2 of them across the screen. But yeah, that would probably be, now again, on this assignment, moving from a 1024 by 1024 down to like 128 by 128 is still probably too big to debug. But the point being is, let's say this was taking a really long time and you just wanted to get a quick result. Running your code on a cropped version of the actual image is probably a lot smarter thing to do than scaling the whole image down. It doesn't matter on this assignment, but here's another reason why. Is imagine that all these different circles were shaded with different code paths. Like one was red and one was blue, and there was an if statement there. Here, you might be like, look, there's no divergence at all because all of these circles, all of these pixels have the same coverage of circles. You shrink it down, you actually just change the SIMD divergence pattern of your actual application as well. So there can be a lot of really tricky things to think about when you're scaling down. Let's think about the other example from last class, which was the n-body simulation. So remember, these particles are moving around over time. How would you scale this particular application down? So remember, the parameters are the number of particles, the grid size, really n is the number of particles. Theta was how accurate you want the cutoffs to be. Delta t is the time step, the number of time steps in the simulation, and t is sort of the total number of time steps. So if I wanted to make this a really small program to be able to run through my simulator or maybe to debug, which of those variables do you want to begin to maybe shrink? What's the easiest one? Yeah, so the easiest one is if this application used to run for 1 billion time steps, well, let's just run it for 100 and see how that goes. That seems pretty easy. What's the pitfall with that approach? That's a good approach. That's where I would start. But what did you remember in the videos that we had? The videos that we watched about these simulations might suggest something. And I think I can, well, you guys all remember the video? Yeah, so what might be a problem with saying, you know what, I'm just going to run the first 1,000 time steps, not all 10 billion of them? Right, at the Big Bang, the distribution of the universe is very different than it is today. And the distribution of the particles is absolutely salient to the performance of this program, right? So if you happen to choose the very beginning or the very end, that might not be representative of the whole thing. So you might want to choose segments at various slices throughout the simulation. Exactly. Because like this thing it starts out very uniform or maybe at one point and then begins to clump up, and that will change how your program works completely. Okay. So again, like there's no real science to this. I just want to make everybody very aware that as soon as you get out of a realm where I'm providing you a grading harness, you need to think very carefully about what you're doing when you're scaling up or down. Okay. And that was the takeaway here. It can be very tricky, so be careful. So in light of that, I want to close the lecture on some tricks that can be very helpful to you in debugging your parallel software. And somebody asked me at the beginning of this lecture, I love the comment, I can't remember who it was, well, how do we know if we did a good job at all when when the curve was curving back down, right? Well, let's think of it. How do we know if we're doing a good job at all? Well, first of all, and what I tell everybody that's coming to my office hours is, please get working code, measure it, and then figure out what your measurements tell you is wrong. There have been a lot of people that have come in with these elaborate, we're going to do this quad tree, and then we're going to do adaptive parallelism, and we're going to distribute perfectly. And I'm like, do you know that that even matters? Right? So an assignment 2 is a really good example of get it working, measure your code to figure out what part is slow, and then react to those measurements. So the question is, well, how the heck do we actually make those measurements? So, or how the heck do we know how close we are to really good if we don't have checker.pl, which you often don't have in life? So one thing that I always like to do is I like to ask the question, am I bandwidth bound or am I compute bound? That's often the first question that I like to ask myself when tuning these programs. So what would be a sign? Well, actually, I won't even go in that direction. And the reason why I want to know if I'm bandwidth bound is, or the reason what I do is I try and figure out how much bandwidth am I using, and is that relatively close to what I should expect on a particular machine. So here's a graph that was made by some folks at Berkeley. And what they did was, well, you can go read the specs of a machine, and it might say that the peak flops is this, or the peak bandwidth is this. And in practice, in the real world, it's not always the case that you're able to obtain all of that peak bandwidth, right? And you've seen this in both part 1 of assignment 2 as well as parts of assignment 1, where you're like, look, it's pretty much bandwidth bound, but we're actually only at about 75% of peak. And to get the rest of it, I would have to work so hard that I'm just going to consider it I'm getting peak. So these folks actually wrote a program to try and figure out when they were bandwidth bound. So I want you to pay attention to just the blue line for now. The 2 lines are 2 different computers. Well, let's just look at the blue line. And what they did here is they say this is the rate at which they were performing instructions. So this is operations per second as the program was changed. These are all different programs. And the programs differ in that their arithmetic intensity is different. So this program says that we're going to load 4 values and then do 1 math op. This is load 2 values, do 1 math op. This is load 1 value, do 16 math ops for every value you load. So the arithmetic intensity is getting higher and higher and higher as we go down the x-axis. So here's the question. At what point is the program compute bound? And you can read it right off this graph. Sorry? So you're saying that this plateau, the roof line, as they call it in this paper. So what do you get? What made you conclude that? Why is the performance of the program going up, the throughput going up, as I write different programs, and then as I add more and more programs that have more and more math, the performance, and when I say performance, I mean the throughput. Why does it stop going up? So you correctly, I agree with your assessment, and what was your reasoning? This is the maximum throughput that this computer can perform instructions at. So why were we not achieving that throughput in this realm over here on the left-hand side of the graph? Okay? Bandwidth bound. Okay, so okay, and that's absolutely true. And now somebody explain to me why that's the what is bandwidth bound is terminology, and I want to move away from this correct terminology. But what is actually happening here? Yes. So the rate at which we are trying to feed the instruction pipeline with data is not high enough, meaning that the instruction pipeline is idle a whole lot. So I'm here spinning my wheels at you know, I'm eating food at 10 hot dogs per minute, and the memory system can only provide me hot dogs at 5 hot dogs per minute. So half the time, I'm just sitting here waiting, which means if the memory system speeds up, or in this case, you can't speed the memory system up, if we change the program such that there's more math for every load, that just gives me more work to do, so my effective throughput, the amount of time that I'm waiting, is less until this point here. And what does this point here mean? We said the term compute bound, but what did that actually mean? Why can I not go any faster? The ALU pipeline is executing whatever it can do every clock. It's completely full. Is memory busy? Is memory saturated at this point? It may be, but it's actually probably not, right? Because now memory can provide data at a much faster rate than it's needed by the ALU pipeline. Okay, so what does this, so good. So this tells you that if you have some other program, and that other program you can somehow measure that the instructions per second or operations per second is anywhere near this line, that means you're probably done. There's not much else you can do. So what happened here in this Opteron X4? What do you think? So that's a different computer sharing the same memory system. So it's a different processor in the same box. And what would you say about that processor? Yes. Yeah, and specifically, how much more throughput can it sustain? 4 times more. It turns out that this graph is slightly confusing. This is a 2-core processor. This is a 4-core processor, and it just turns out that the 4-core processor can do twice as many instructions per clock as the 2-core processor. So that's why it's 4 times faster. Why do you observe that this the X4 is bandwidth bound in a much larger realm of scenarios than the X2? Well, it's 4 times faster. It can do 4 times more instructions per second. Yeah, with just 2 more cores. Yeah. So it's 4 times as fast. And that's why you see this throughput being 16 and this throughput being 64. So why is it the case that this processor flattens out here, and this processor keeps going up and then flattens out there? Yeah. Yeah, exactly. Exactly. So this program, the same program running on these 2 processors, is going to be bandwidth bound in the green scenario and compute bound in the blue scenario for that reason. Good. Okay. And so you're doing well if your program is over here. If your program has an arithmetic intensity that looks like any of these, then you're going to be compute bound on the blue processor. And there's nothing else you can do to run any faster other than change your algorithm and do less work. Good. And so here's an example of doing more work to do a little bit better. So all of these are little curves that kind of look like this. And they started writing some more micro benchmarks to try and figure out how fast they can go. So this compute, this line right here was the peak rate of some processor, like with C code. And then what they did is they actually changed their code to be SIMD. They vectorized it, which increased the throughput of the system by a factor of 4, because it was 4-wide SIMD. So by writing better code, they said, well, if you don't SIMDize your code, you should expect to be here. If you do SIMDize your code, you should be expect to be there. And then the third line is where they did some extra tricks for trying to get very good in integer versus floating point instruction issue, just some additional code optimization. And then also, they made some optimizations that moved this curve in this direction. And so this was, they used prefetching. They used various other types of instructions to get the most out of the memory system. And these are the kinds of things that would have given you extra credit on assignment 1, part 5. It would have been these very complicated instruction level things. So they wrote all these micro benchmarks to figure out what is the best you can possibly do on this computer. And then whenever you have an application, you can cross-check that against those numbers to figure out, oh, it looks like I'm likely very bandwidth bound. Or I'm very much at the peak rate that I've ever written like a program at, therefore I'm compute bound. So here are a few examples of trying to figure out what's slowing you down. For example, if you want to know if you're bandwidth bound, or if you want to know if you're compute bound, just go add more instructions. And if your program gets slower with those instructions, that means you're probably limited by the rate at which you can issue instructions, which means you're probably compute bound. If you think you're bandwidth bound, you can actually remove all the computation and see if the performance of your application stays exactly the same. Because if you're bandwidth bound, it doesn't matter how much you compute, the performance will roughly be the same. If you think you're limited by locks, count the locks. See if performance changes. So these are the types of simple debugging tricks that a lot of people use to kind of get a sense of, well, how well am I doing? And of course, there's a whole bunch of very useful profiling tools and stuff like that that people can use as well. And we encourage you to kind of just get online and learn how to use those kinds of things. So yeah, so some programming tools that you might really like is that, for example, on Intel processors, there's VTune, which is a really advanced, almost too advanced to be useful most of the time, tool. There's Intel's performance counter tool, which allows you to actually query the system for some very interesting performance counters, like how many times was there an L2 cache miss between this point and this point. So there's no shortage of detail that you can get from modern tools. Something even simpler is like something like, I can pop open Activity Monitor. And if I go to Window CPU history, we can see what my CPU is doing, which is not much these days. So first of all, this is a quad-core laptop. Notice that my CPU history has 8 visualization slots in it. 1, 2, 3, 4, 5, 6, 7, 8. Why is that? I have a quad-core laptop. That is the two, from the operating system's perspective, there are 8 cores, right? There are 8 execution contexts which the operating system can put processes on. So you see those 8 cores. Let's see. So, for example, I wrote this program called PEG CPU. And my PEG CPU program does exactly that. It creates 8 threads and just kind of like spins doing some math. And I'll run it for a little bit, and you can see that that's in fact what it does. It's well named. Okay. So CPU got busy. Now notice that let's go ahead and drop that to 4. Notice that those 4 threads are running. Why don't you see them? Why didn't it use the top 4? Sorry, one second. What was that? Why didn't my program use the top 4? Why did it spread it's an odd choice, right? Let's see if it actually chooses, operating system can choose whatever it wants. It looks like it's choosing the same this time, okay? Yeah, so these are virtual cores 0 through 8, and we can pretty much assume that 0, 1 are hyperthreads on the same core, 2, 3 are hyperthreads on a different core. It's very possible that the operating system might decide to move one of these at some point. It could. Well, we can see. I suspect you might see a little bit of variability in what the 5th core ends up being. Let's see. Pretty interesting that the 5th one, that's interesting. So OSX is bouncing the 5th one, that 5th thread over a bunch of cores. That seems like the wrong decision. Or no, actually it doesn't seem like the wrong decision, because if I was an operating system scheduler, I would say I have 4 threads pegging the CPU on all my 4 cores. I have a 5th thread, and maybe I'm going to try and over time distribute the load of the 5th thread onto all 4 of the physicals. Right? Yeah, I was just doing math. The red is going to be kernel time. I don't know why it's spending any time in the kernel, but who knows? Yeah. No, with 3, it's almost certainly going to just keep them pegged, right? Because I believe what the operating system is doing is it's trying to keep equal amount of CPU time onto all 4 of the physicals. Did I not build that? I think I built it. Yeah, that's interesting. It's an interesting schedule. So here's a few more actually curious. Let's go watch, what do we want? YouTube, I don't know, Grammys. So let's watch a video. I'm going to turn off my speakers. Whatever. Oh gosh, that's not what I wanted. Oh, it's like Beyonce's performance last night, right? Okay, so look at the CPU load. It's surprisingly low, right? Red is kernel. So quite low. Playing video. Full HD video. Anybody have an explanation for this? And in fact, I can actually do something different. Let me go ahead and shut down Chrome just to get all threads, as many as I can out of the system. Let's go to, let me just play a local video. Okay, I know there's a video here. So here's playing a local video on my machine, not even through the browser. This is an HD video. Notice that there's like no CPU. Not sure what that is. But essentially 0 CPU now, because now I'm not even involving Chrome. So can anybody explain that? That is correct. We won't talk about this too much until a later lecture. But can anybody explain that? Yeah. So H.264, or video decode these days, it's a very, well, video encode and decode is a very expensive operation. But it's also one that's sort of set in standards. People don't change very often, and when they do, the entire standards body figures out what H.265 should be. So video decode and encode on any modern platform in 2017 is performed by a separate video decode only processor. So it is a fixed function processor actually taking on that responsibility, which is why I can play movies out to wazoo on my laptop and not burn CPU, which is great, but also burn a very small amount of energy. So it's not even your processor handling that part of it. Yes. I mean, these modern ASICs support a lot of formats, and about anybody encodes their